There's an old saying that everyone is entitled to their own opinions, but not their own facts. The idea behind this sentiment is that we might disagree on the importance we assign to various aspects of a problem, whether personal, societal, or scientific, as well as on what ought to be done about that problem from an actionable standpoint. However, in order to have a meaningful conversation about ethics, policy, or our approach to solving or otherwise addressing such a problem, we all have to share the same factual reality, at least by agreeing on what the facts of the problem actually are. Here in 2025, unfortunately, verifiable facts are often countered with untrue narratives that stem from motivated reasoning, with many groups denying factual reality in order to promote policies that are at odds with those established facts. Some even point to Einstein in defense of this approach, noting a quote that's often attributed to him: "If the facts don't fit the theory, change the facts." In the aftermath of the rise of alternative facts, a term popularized by American political figures in early 2017, this now appears to be the modus operandi of an enormous number of institutions, including the NIH, the CDC, the FDA, the EPA, the NSF, and even NASA. However, Einstein never made such a statement, and in fact what he actually said implies the exact opposite of disregarding facts that undermine one's preferred narrative. Here's the truth behind Einstein's actual "change the facts" quote. Einstein is one of the most towering figures in not only the history of physics, but in all of science. In the early 20th century, he made extraordinary contributions to our understanding of reality, including determining that the speed of light, not distances or durations, was the one constant that all observers agreed upon, discovering the equivalence of mass and energy through his most famous equation, E=mc², explaining the photoelectric effect through the quantization of energy in the form of photons, explaining the random-seeming microscopic motions of particles, Brownian motion, through the kinetic theory of molecules, reframing our understanding of gravity as the curvature of space-time caused by matter and energy, through his general theory of relativity, probing the foundations of quantum physics through the Einstein-Podolsky-Rosen paradox, co-discovering the behavior of the statistics of integer spin particles, Bose-Einstein statistics, developing the precursor of the idea of wormholes through Einstein-Rosen bridges, along with many others. In particular, his novel theory of gravitation, which was put forth in 1915, would go on to replace Newtonian gravity as our most accurate and powerful description of this all-important cosmic force. Einstein was able to show that his theory, which insisted that mass and energy curved the underlying fabric of space-time, and that it was that curved, not flat space-time that dictated how matter and energy would then move, could reproduce all of Newtonian gravity's successes, explain the advance of the precession of the planet Mercury's perihelion, which Newtonian gravity could not do, and would make distinct predictions from Newton's theory in multiple ways. Although those first two facts, reproducing Newton's predictions in the weak field regime, that is, at large distances from approximately point-like masses, and correctly accounting for Mercury's orbit where Newton's theory could not, provided extremely strong motivations for considering Einstein's then new theory as superior to Newton's, it would require an additional novel prediction that we could actually go out and test and measure to evaluate Newton's versus Einstein's theories head-to-head. The one prediction that Einstein and his supporters suggested most strongly would appear when it came to the bending of distant light sources that passed near sufficiently massive objects. We're probably most familiar with this phenomenon today in the form of gravitational lensing. But back in the 1910s, we didn't even know that there were objects out there beyond our own galaxy. The leading thought was that the universe was static, stable, and was all contained within the entirety of the Milky Way. So instead, the suggestion was to wait for nature to give us the opportunity to create a configuration where such a situation would be observable during a total solar eclipse. The thinking went that during most times, the stars are only visible at night, and so we observe their apparent positions during circumstances where there's no major source of gravitation deflecting their light. But during a total eclipse, the stars that appeared nearest to the now eclipsed sun would be bent by the sun's gravity, distorting their apparent position in a quantitative, measurable fashion. Acquiring these key observations was made clear as a scientific priority practically as soon as Einstein put forth his finished theory in its final form, in late 1915. However, the short time until the next solar eclipse in 1916, coupled with the outbreak of the Great War, now known as World War I, made such an expedition to observe it an impossibility. The next one, in 1918, occurred coast to coast across North America, and an expedition that was sent to make those critical observations was foiled by clouds at the critical moment, setting the stage for expeditions to South America and Western Africa for the next total solar eclipse, the one that would critically occur in 1919. That eclipse was a special one, as it was one of the longest total solar eclipses that can occur on Earth, leading to the darkest skies and the greatest observing conditions for stars near to the limb of the sun. Clouds weren't an issue this time, and observations acquired from Brazil and the island of Principe were successfully analyzed to determine whether, and by how much, light from the background stars was deflected by the gravity of the sun. Although the results and conclusions were contested by many skeptics, the evidence was robust and overwhelming. The sun's gravity did indeed deflect that starlight, and by the amount predicted by Einstein's and not by Newton's theory. General relativity had passed the critical test. It was later in that year, in the fall of 1919, that Einstein was having a discussion with a student, where Einstein shared with that student the results of the Eclipse expedition, results that confirmed his general theory of relativity. The student then asked what Einstein himself would have done if the results had come in and hadn't confirmed his theory. Einstein's response, as recorded by the historian Abraham Pius, was, "Da Coent mir halt der liebe Gott leid tun, die Theorie stimmt doch." The translation of this statement into English is roughly, "Then I must pity the dear Lord, the theory is still correct." Note that this is very different in both style and substance than the statement, "If the facts don't fit the theory, change the facts." It is one thing to be convinced that a great novel idea is correct, even if the data and evidence is not yet sufficient to convince a skeptical onlooker of its veracity, which is a situation that many who put forth novel, powerful ideas find themselves in. They themselves may be convinced of their ideas before the critical evidence comes in, and sometimes they're right. Einstein was confident that his theory was correct, but in order to convince others, the evidence needed to support him. Fortunately for Einstein, it wound up doing precisely that. Similarly, Dirac was convinced of the presence and reality of antimatter, as predicted by his theory of holes in the Dirac sea. But the remainder of the community wouldn't be convinced until there was experimental confirmation of the presence of such particles. Schrödinger worked out a method for calculating the energy levels of the hydrogen atom in 1925, and while it gave predictions that were largely in agreement with experiment, there were small departures that frustrated him and made him hesitate about publishing his results. He finally decided to do it, and the discrepancies were later explained by Dirac with a fully relativistic formulation of the quantum mechanics of the problem. Sometimes it turns out that experiments and observations aren't to be trusted, as follow-up experiments don't always lead to independent confirmation of the initial results. Other times, theorists are convinced that their ideas are going to be correct and borne out by reality, only to be met with disappointment when the critical results come in. Grand unification was a remarkable idea, but its prediction of an unstable proton has yet to be verified. The proton has never been observed to decay. Supersymmetry was another remarkable idea, but its absence in accelerator experiments is the most notable feature of that theory. In the end, it is by putting the question of reality to nature itself that teaches us what's scientifically true. So where did the interpretation that Einstein said, "If the facts don't fit the theory, change the facts," come from? It can be traced back to a 1958 article in Product Engineering that said, "There is an age-old adage, if the facts don't fit the theory, change the theory." But too often, it's easier to keep the theory and change the facts. Unlike the version misattributed to Einstein, the actual original version actually highlights something profound about how we reason. When we get mentally fatigued, often by a problem being more complex than we're prepared for, we instead resort to a simpler explanation, even if that explanation is insufficient to explain the actual facts at hand. We can even go so far in our quest to not have to consider too much complexity, to throw out the facts that are inconvenient for the explanation we've wedded ourselves to, and change the facts to fit our narrative, rather than to scrupulously test whether the facts fit the theory or not, and to evaluate the validity of that theory accordingly. It's a manifestation of what fiction writer Libba Bray wrote about how you convince people of an untruth. "You must remember, my dear lady, the most important rule of any successful illusion. First, the people must want to believe in it. In an era where many of the thought leaders and decision makers in our global society refuse to accept the actual facts of reality and instead argue from a counterfactual position that supports their preferred narrative, this isn't just a problem for practicing scientists. Instead, it's a problem that has infected all of civil society, and that brings along with it great dangers to public health, human safety, and the long-term prosperity of entire nations. For those of you who want to do something about it and not to succumb to these counterfactual illusions yourself, you might consider asking yourself the following 2 questions. First, ask yourself critically what the key pieces of evidence are that, when you put them together, that have led you to the position you currently hold as respects any problem or question at all. If you can articulate those points to someone who might disagree with you, you not only gain the opportunity to change their mind based on those facts, you also give them the opportunity to share their own key pieces of evidence that might support, undermine, conflict with, or refute the evidence you yourself have put forth. Either way, this free exchange of information and ideas, where all participants are committed to telling the truth about reality, is a way to increase knowledge and understanding in the world. After laying out the key pieces of evidence brought forth by all parties, you still might find you don't inhabit a shared reality, where everyone agrees on the veracity of the facts put forth thus far. That brings us to the second question to ask of not only yourself, but of everyone earnestly participating in the conversation. What definitive piece of evidence could we gather that would settle the issue one way or the other, in a way that would be satisfying from an evidence-based perspective? For a few examples, if a small plane flew behind an alleged chemtrail delivering plane and collected and measured the composition of all the molecules in the exhaust, would that allow you to decide whether chemtrails were real? If a small plane flew behind an alleged chemtrail delivering plane and collected and measured the composition of all the molecules in the exhaust, would that allow you to decide whether chemtrails were real? If you tracked the level of ingested fluoride over a large population and correlated them with long-term dental and medical health outcomes, would that convince you of either the safety or harmfulness of fluoride? If you tracked the level of ingested fluoride over a large population and correlated them with long-term dental and medical health outcomes, would that convince you of either the safety or harmfulness of fluoride? If we could accurately measure the global average land/ocean/surface temperature, the changes in our atmosphere's contents, and the absorptive radiative properties of every one of the gases in Earth's atmosphere, would that provide decisive evidence as to whether humans are warming the planet? If we could accurately measure the global average land/ocean/surface temperature, the changes in our atmosphere's contents, and the absorptive radiative properties of every one of the gases in Earth's atmosphere, would that provide decisive evidence as to whether humans are warming the planet? The key, in each instance, isn't to change the facts to fit our preferred theory. It's to gather sufficient evidence that we can determine which theory, idea, or explanation best fits the full suite of data at our disposal. We have to be especially careful in today's modern world not to simply take the word of a lone expert or a person in a position of power about the facts about reality. We instead need to be able to verify those facts for ourselves. With so many contrarians, including experts and non-experts alike, in high-level positions of power, and the ability to misinform millions of people while simultaneously making decisions that could lead to death, disease, and other incalculable harms, it's more important than ever to demand that we wed ourselves to reality and follow the evidence wherever it may lead. We oversimply reality and ignore facts, not just at our own peril, but to the peril of all others who rely on our collective ability to get these decisions right. As virologist Robert Burioni so eloquently put it back in 2016, when brought onto a TV talk show with 2 non-expert anti-vaccine advocates, the Earth is round, gasoline is flammable, and vaccines are safe and effective. All the rest are dangerous lies. We must remember that, when it comes to debate, the goal is not to convince people that your side is right. That's often the outcome of a debate, but that doesn't always equate to success. For in a successful debate, the ultimate goal should be to expose and uncover the truth about reality, whatever it may be, and to have that truth serve as the foundation for any policy decisions that follow. After all, this is how the enterprise of science itself advances, as Carl Sagan noted back in the 20th century, with the following sentiment. In science, it often happens that scientists say, "You know, that's a really good argument, my position is mistaken." And then they would actually change their minds and you never hear that old view from them again. They really do it. It doesn't happen as often as it should, because scientists are human and change is sometimes painful, but it happens every day. Here in 2025, the truth of reality matters more than ever. May we find it within ourselves to accept nothing less.